Okay, so I'm in between, I would say, a drink and Sebastien. So I will keep it short. I will be more static than Frank, which is not difficult because Frank dances over the podium, so I cannot do that. But to add to my bio, I recently joined the NRB pizza team, even though I didn't see pizza yet at NRB, but in summer they gave us some Belgian fries. They had a food truck coming in, so I joined the Belgian fries team in June, and I'm implementing a test automation, I would say solution implementation for mainframe development. I will talk today about containerization and why would you want to use containers on Z? Why would I care about containers on Z? What is that? If you look at the challenges of today, and I'm not going to repeat the separate points because we heard them all. Every speaker that we heard this afternoon was talking about the development challenges. And containerization is not necessarily only about development. It's also about containerizing your runtime, your applications, run them in separate boxes if you want, in separate containers. But I use development as a good example of how you can eventually containerize your development infrastructure in a containerized way. So like I said earlier, if we look at the challenges of today, it's all about complexity for the developers. They don't develop nowadays in one language. Every language often brings its own IDE. That means that a developer has to move quickly from PL1 to Java, maybe. Yeah? That's what we heard this afternoon as well. Maybe it are two different developers that have to work on the same solution. So it's all about the complex, and if every developer has to have the software on its own laptop, it's not easy. So let's think about how to make that easier with containers. If we talk about containers nowadays, we have to talk about Docker, right? So if we hear about containers, we hear about Docker, and they talk about Kubernetes. The definition of a container is what Docker says, and I'm going to read their statement. It's like, containers are standardized units of software that allows developers to isolate, and that is very important, that isolate their application from its environment. So, and that's just to solve, it works on my machine, so if I put it in production and it doesn't work there, that's somebody else's problem. So the fact that you can containerize your application and also your development, because my example that I will show you in a second is about how IBM is containerizing the development complexity in a container, Docker is a de facto standard for containerized applications. If we look at evolution in IT, and you go from the development process, you see that, and we heard that also this afternoon, is that we are moving forward. We are moving forward from a waterfall way of developing to agile, and nowadays we are talking about DevOps. Same is true for application architecture. I think Aymeric and Sebastien were talking about that as well, moving forward from a typical monolithic application developed in PL1 and IMS. They are moving forward to a complex architecture where they mix up Java and PL1 in a microservices way of executing the application logic. And if you look at the deployment packaging, we are moving forward from physical servers, like many years ago, to virtual servers, which was still virtualizing on physical machines. Now we are moving forward to containers. And then in the context of NRB, of course, we are moving from a typical data center where even every company had its own data center. We're moving to a hosted data center, and now we are moving forward to a hybrid cloud solution. And does that mean that one is replacing the other? No, it's probably the right answer is probably a mixture of all the solutions together. Like I said, I would like to share with you a little video on a beautiful example of how IBM brings forward, and this morning No, this afternoon, very short after the lunch. Adam mentioned Wazi developer. This video shows you how IBM is introducing development in a containerized fashion. So I don't know if I can just play the video. No. Can somebody click on the play button? Thank you. Yeah, you have to click on the play button. It's a link to well, let's not, I will just continue without the video. So you will get the presentations, I suppose. You can play the video on your own. In the next slide, this explains more or less what Wazi developer is. In fact, as Adam already mentioned to it, it gives the developer the possibility to request his personal development environment in a Red Hat OpenShift environment. So the developer doesn't need to have a pre-configured and pre-installed laptop where he can start his IDE. In the context of NRB, it will be Topaz. He doesn't need all that. He just requests in a browser, a user interface, I want my development environment to be kicked off. So that's what he does. Then the developer can choose. In that context, he can choose what IDE would like to use. You have young developers that prefer Topaz, which is an Eclipse-based IDE, but you have maybe developers that come from school and prefer VS Code or Eclipse-J, which is a browser-based Eclipse-based IDE. So a developer can make a choice of their own IDE. Even developing PL1 applications and or Java applications, they can have a choice of their IDE. The fact that we are using the same SCM, so Java developers are using, in the context again of NRB, are using GitHub or GitLab. They are using in any way SCM, which is typically eventually a cloud-based SCM. In the context of NRB, it's on-premise. But the mainframe developers today are using ISPW. Maybe we will have to look how we can bring the PL1 applications also into that Git repository to have the same process for all the developers at once. Which doesn't mean that we are moving away ISPW, because ISPW is typically a very good tool to deploy, right? So even if the source code is not in ISPW, you can still use ISPW to make sure that the deployment happens correctly. In that context, your development environment, sorry, your Wazi development environment, which is a containerized development environment, has already the CI/CD pipeline integration completely pre-configured. The developer doesn't have to think about, I have to make a connection to that repository and I have to check it out from that repository. I have to create my own repo, and then I have, so it doesn't have to think about all that, because in the container, it's all already pre-configured. It's there to be used. And then we think about something that is called Wazi Sandbox. Wazi Sandbox is, in fact, ZDNT in a container. For those who don't know what ZDNT is IBM Z Development and Test. It is, in fact, a full ZOS running in an x86 environment. So it's emulating your disks. So that Wazi Sandbox could be, I would say, a personalized LPAR for the developer to do his testing when he needs. So the fact that you have multiple releases might give a complexity of, I'm using the database version 5, and for release next after me, we are using database version 6. So in that context, the real ZOS has a problem, because it's very difficult to distinguish the different versions. If you have a personalized testing environment where you can bring in your data, and with test data management tools, you can even preload your data in anonymized way, so that the data is not, thanks to the GDPR regulations, that the developer doesn't need to see all the data that comes from production. So that's an example of how you can containerize your development environment. And of course, one thing I forgot to mention, but that is very important for the NRB customers, is if you can containerize your development in a non-ZOS environment, you will reduce your MIPS consumption, which will of course reduce your MLC cost as well. So in that context, developing in a container becomes important and makes it cheaper I would say, use the mainframe. And therefore, I'm very proud and happy to introduce Sebastien, who is going to give you more details about how IBM is doing containerization on the Z platform.
Thank you, Paul. Hello, everyone. So, what I would like to start with is really to say that we are invited to the party. The thing is, when we looked, in fact, on the right, on the top here, we are seeing the cloud native, which is happening in the cloud. So all this transformation around the containerization is taking place in the cloud native environment. So today, when you look to Google, Azure, and other environments, this is really the place where all the transformation started a few years ago. And the Z, in fact, was not really invited in that party. And we had the traditional and everything running on-premise. But there has been a shift now today where we can enter the party. We can create environments on a cloud native environment, which is on-premise, hosted on the IBM Z platform. And we can continue the application modernization play while we can take all the benefits of the cloud native environments today. And that's, in fact, some of the elements that I want to share with you here. It's a transformation in that model. Something very important is the position of Z today. From an architectural point of view, we shifted, in fact, the level, I would say, of development, right? When we talk about containers, it means that the entire application, as we're going to see that, can occur, and we have to share those developments inside a same pool of resource. And when you looked into the different systems which are today available in most of the environments, what is the best pool of shared resource we have in the industry today? That's typically our mainframe. So the containers are directly taking benefits from the value we have on all the non-functional requirements which are inherited from this architecture on the mainframe. And it covers a wide range of capabilities. When we're talking about new modern Java applications, we get the Java garbage collections. This is an accelerator for most of our applications. When we deal, in fact, with security, we get microcode on our core today, which are capable to accelerate, in fact, the encryptions of those applications. When we talk about compression of the data, we can have much more communications between all of those containers because we are within the same boundaries, within the same systems. We can use, in fact, a huge number of features and topologies inside the machine that range from the hypersocket network communications we have through the RDMA protocols, communicating from memory to memory. So we have all of the bunch of capabilities inside that box, which makes a lot of sense to run containers on our platform. Another very strong differentiators we have with containers on the Z side is when you look to the distributed world, they got mechanisms like vMotion, right? They can move virtual machines from one system, physical system, to another one, but that needs to go through the wire at some point. If you start to move your virtual machine from one environment, which is an x86 box, to another one, at some point your containerized workload needs to go through that layer. So you increase the latency, right? That's fine if you have a few number of containers, but that's not the case. The trend is really to have a huge number of containers today, and that's going to increase. So putting a lot of pressure on all the distributed environments, where on our platform, we have those mechanisms that helps, in fact, to speed up all the latencies for all those modern applications, right? So there is a huge number of attributes and arguments here on why containers on Z. I could develop a lot of them, but here I would just want to move on, and my focus in that presentation is not on the operations of the containers on the Z. So I'm really conscious about that, but I wanted, in fact, to create that presentation for a Z audience to make people aware of what's going on and what are the architecture of containers outside of the Z box, because that's coming to the Z, and we really need to understand what are the differences, how it's working, so we can then better understand the use cases we have on the platform to leverage, in fact, our existing applications, plus the modern and new applications on that platform. So I will go, in fact, through a number of slides here and I will go through all of them, right? But of course, you can feel free to come back to me to get much more detail on any of those slides. So what is a container? For those of you who know Linux, a Linux operating system is a little kernel, right? And a virtual machine is using a Linux operating system. In fact, the container can be seen as a processus, right? It's a process. This process is running inside Linux, and we are using some Linux techniques, right? Which are based on C groups, which are managing CPU, memory, IOs, right? And which can contain the execution of that processus inside a Linux operating system. So we are capable to isolate with this container technology an entire set of applications with their dependencies. And this is really the key word here, all the dependencies. So the applications relies on binaries and libraries, and typically a container is in fact a piece where your applications are bundled with the binaries and libraries. What it means is then you have a way to move those resources, this entire little application, this little package, right, which is called in fact a container, and to move it from one environment to another one. The key difference we have with a virtual machine is when you are with a virtual machine, you have an hypervisor, which is a common hypervisor for all the virtual machines. And we are embedding the application, the binary, the libraries, within all the entire, what we call the guest operating system. So it could be a SLES, it could be a Red Hat, it could be an Ubuntu, whatever is the operating system. But each time I need to test the entire piece of code for each operating system. It was the past. There are still a lot of virtualized environments still remaining, but we want to move to a different environment where we have the containers, where we have the applications and the libraries, but we don't have anymore this guest operating system that is embarked with the containers. That gives us the flexibility to move those components, those packages which are containers, from one environment, which is an operating system host here, to another operating system host. It means I can be in dev, in test, in pre-productions, etc., so I can move very fast my applications with all the dependencies, right? And that's a real shift in the industry today for all the modern applications. So when we capture that, how to build a container? Pretty simple. As any environment, you need a recipe. So a recipe is started with Docker a few years ago. It's what we call, let's say, a Docker file. So we get this Docker file here. It's a description, right? A declarative, let's say, file where I have a sequence of steps to execute, okay? I have to install this package, I have to deploy, I have to start my applications, and so on. From this file here, I need to get an engine here to build what we call an image. This image for a container, right, it's a binary file, which is stored, right, on a shelf, right? It's called a registry. This registry can host multiple images of different versions of our application. So I can have application 1 with version 1, 2, 3. They will all be stored in that registry. And that the developer which is working with that principle, those processes here, right, to create from the source code the binary images which are pushed into the registry. And then here, then I can take the images from this registry, and I can push those images into my real runtime, okay? So here, I take an image, and I say, I need to instantiate that image. What it looks like is if you have a template, and from this template, you instantiate your container that will have all the instructions and your applications deployed inside that little processes, which is running inside a Linux environment, okay? So I can duplicate very easily those containers. The challenge is to orchestrate those containers. So what is the most common solutions we have on the market today to manage those kinds of containers? Someone has an idea? What is today the most famous orchestrator existing in the industry to manage containers? Very important as well to catch. This is in fact Kubernetes. Kubernetes, right, is in fact the engine to orchestrate all of those containers, all the complexity of creating those little Linux processes that needs to be managed across multiple heterogeneous environments. So what you will find, either in Google or even in Azure or other clouds, IBM as well, and even within our solution, we have some solutions I will describe a little bit later, which are Red Hat OpenShift. It all relies on Kubernetes. So what are the principles of Kubernetes? Very simple, right? We have here containers, specification, okay? And inside this container here, we have our image, environment variables, or even some storage links that we are embedding into this specification. And this is running into what we call a pod environment, okay? And everything is part of a replica set, which is capable to duplicate how many pods you want to run. So you can scale each container independently. So you could think from your applications to have multiple components. Each time you create that little pod here with your applications or one element of your application, you can scale it very easily. Okay, so we have this environment which is all into a deployment. Okay, then the architecture of a Kubernetes environment, right, that will sit in fact on our Z-Box is pretty simple. Either you can access it through a user interface or either through a command line, but everything goes through a set of APIs. And these APIs connect you to what we call the Kubernetes Master. So inside this Kubernetes Master, right, we are communicating with what we call worker nodes. These worker nodes are in fact Linux machines, right, which are running and executing those containers. So most of the containers you have in the industries are running today in those worker nodes, and we are accessing those applications, those new applications inside those components. And they are managed by this component, which is a Kubernetes Master. If I'm opening this box, in that Kubernetes Master, we have a configuration file for my cluster, which is a distributed file across multiple worker environments, multiple masters. And then you have API server, scheduler, and controller, which are managing those environments and those containers. And if we are opening now the worker nodes, inside the worker nodes, we are seeing that we have all our containers, and we have some components here, like the kubelet engine, which is an agent that the Kubernetes Master is going to use with the worker. Okay, so quite simple, I would say, in terms of architecture. But this change here, I'm not going to describe this reference architecture for the containers, but what you have to know is that everything is going through the kubelet agents, communicate through, in fact, this global resource control protocol here we have, right? Which allows to communicate with what we call a créé runtime. This is a runtime specific for running the containers in today's environments. So, just to recap very quickly, we get a container. This container was Docker, but today we are using Podman, Builder, créé, which are the new runtime you will heard about from the distributed team working with you on those technology. From the container, we need to have an image. We can have a registry where the images are stored in different versions. From one image, I can deploy multiple pods in environments which are my Kubernetes environments. And in order for an application to find the right container, there are other attributes, other components which are part of the containerization part. We have what we call a route here that defines for my application here, how can I access, to the service. So this route is linked to a service, and this service has some tags in the front end, which allows me to identify what are in fact the containers to address. Okay, very simple. What it means is any of those containers can run on any environment from a physical point of view. It means that this container can be on one Linux system, this one on a second system, and this one on a third system. Okay, so if this one is failing, my applications continue in fact to be served. So all the mechanisms for high availability and routing and all the things are embedded with this architecture. So the containers using these architectures are kind of using all of these mechanisms. And there are, of course, mechanisms to allow access to specific user or to restrict the access to different environments, right? So I could say that these developers here are only access to the payment development applications, that's all. And you will not be able to make deployments to the prod or to see the inventory or see the catalog. So there are also some rules to manage and policies to manage those containers into those environments. Okay? One very important notion, I mentioned it is a binary. So you may have a lot that those containers are portable everywhere. That's not exactly true. What's happening is each binary needs to be built for a specific hardware architecture. When I'm building in the process that I show my container, my image, if this is an x86 image, I cannot run that image on an S390X architecture on my Z, right? I need to build another image. And from that binary, then I can deploy it on my platform, right? So very important here, container must be rebuilt from a Dockerfile or different mechanisms on a different hardware platform, okay? So the question, how we can build a single container image that can run on different architecture, I'm pretty sure you're thinking to that point here, is using what we call specification, which is a multi-architecture specification. We have a way to specify that this container here in this environment here, right, can be deployed to point to multiple images and binary images. So I could create my application, which is app1, right? And my application app1, if a developer wants to use it, he will just say, I want on the registry to retrieve app1. And now that I got app1, I want to deploy app1 on my distributed environment on x86. Using that manifest file, we will point to the right, let's say, image for the x86 platform. If my target now is a Z environment, I will take the other image here, which is for the architecture S390X. So I can have one source code, one pool with one single name, but during the deployment, I will pick up the right binary image in the registry. Okay? Okay. So there are a number of commands here on how to achieve that. These are on the presentation. Let's dig into this. Just one point on the architecture development concern. What it means from a containerization point of view and the Z side, what you have here is a binary image, and this is the architecture concern zone. How you're going to address that cycle of development here, because you have two separate streams, right? And that's one of the things where tools like Jenkins, for instance, which are building in fact a pipeline, could be used. So you could create in fact some workflows within Jenkins, for instance, and having in fact to build pipeline for your x86 environment and one for the S390X. So you're using the common tool, you just have a different pipeline that generates your containerized images, and from there you could deploy those images, and this is a common then process across all the environments. Okay? So what is portable and what is not? Of course, there are a lot of discussions on the criteria and the selection of the parts of the application that needs to be containerized, but mainly what you have to keep in mind is a lot of those components here are what we call stateless sessions and stateless services, right? It's not really convenient to let's say, containerize, for instance, a database, right, which is a stateful component. Most of the time, even if we can do that today with some of the storage, which are shared across the clusters, we can do that. But typically, that's in fact the scalability aspect we're going to look at. We're also going to select a number of services which are independent from all the others, because like I said, we can scale those microservices. So if I have my containers, I can decide to have 10 examples of one particular components, because that's, let's say, a component that I need to go through, and this one needs really to scale as a front-end component. So very easily, I will pick up a containerized environment for this particular component of my application, right? So there are a number of criteria to look into, and most of the time, this is when you have very independent, right, components. So this is part of the service-oriented architecture work that needs to be performed, which operations functions need to be exposed in the current environment. So we can identify that with this environment here. Okay, so the solutions to host these containers on the Z side now, right? So here, I like this one because it said here, which server reply faster and is the most secure? And then you have the guy, AWS, no, Google, no, and one said localhost. And here is what's happening, all right? But he's right. That's the fastest one, and that's the most secureable server. So if we have our Z box there, and we could deploy those one here, really, those containers can come to the platform. And today we have all of those solutions here to run the containerized environment. From an architectural point of view, we have traditional legacy APIs here, of course, that we could use and plug directly to our standard, let's say, programs, which are Kix or AMS, GB2MQ, and so on. But on the top here, we have a new environment called ZOS Container Extension here, where we can run containers directly inside the ZOS environment, right? And here we have the new languages that Frank just described in the previous presentation that we could use as well, right? And we can have the standalone as standalone languages in development, but also included into the container extension part. So a full ZOS solutions with modern types of applications, and we are invited to the party of the cloud native development. The other thing here is Linux on Z. You could use and deploy with Red Hat OpenShift, which is one of our solutions that is running on Linux on Z today, which is fully supported. And then we have this solution very secured, which is called HyperProtect Virtual Servers. Right? That's another solution we have to run those. And in the public cloud, we have also those HyperProtect Virtual Services, or even the OpenShift environment that could sit there. Okay. So if you want to dig into those solutions, I will not detail all of them, but you have to be aware that we have the HyperProtect services hosted on the IBM cloud. Some crypto services are available there, right? So you could create, in fact, crypto domain there, and you could use that for digital signatures. So there are a number of use cases where if you want to create an hybrid cloud architecture, you may have to consider these types of offerings we have today. We have database as a service, so this is Mongo database or Postgres database services that you could use. And we have this little yellow here squares that I make, which is the HyperProtect Virtual Servers. And I'm highlighting this one because this is offered in the public cloud, but also on premises, right? So we could deploy this as an appliance, is a fully secured appliance, encrypted, where you can run, in fact, your containerized workload on premises, okay? And then we have some plans here to deliver the Kubernetes, of course, services, like I mentioned, which orchestrate the entire set of deployments, okay? What makes a difference is between this Linux server, which is quite simple, to this one, we are seeing that a logical helper with HyperProtect is using the secure service container capability, and we are isolating in Linux little virtual machines all the workloads, and each machine is isolated from the other. So even if an attacker is getting to the Linux kernel, I cannot get access, in fact, or corrupt the other processes running close to it. So real isolation there. So that's really the benefits of running this kinds of environment for very critical, secure, and environment where we want to really protect the data while modernizing the platform. The other solution I described is Red Hat OpenShift, right? So one of the value points of Red Hat OpenShift is that it can run on many environments, right? I worked on project with customers that are using Azure. They got OpenShift deployed there, and they decided to deploy OpenShift on Linux and Z to access, in fact, to their ZOS environments, right, and their programs. It's a settlement applications, and they built, in fact, this architecture, right? So, and that's one of the value of having the OpenShift Red Hat environment today in this solution. So, like I said, Red Hat OpenShift running on Linux and Z, it's deployed over a Kubernetes platform, right? And we are providing the cluster services, application services, and development services. Everything of those services here are part of the Red Hat OpenShift platform. It means you don't have to reinvent the wheel. You just have to deploy your Red Hat OpenShift cluster on the Linux on the environment, and you can deploy your containers. You take benefits of all of those services, and this is really the value of having the OpenShift clusters and environments running on the Z platform today. And here is a view, right, of an entire full kind of deployments. We have traditional Linux on Z applications. Some of our customers are using Oracle database or some of the analytics workloads that are warehouse hosted there in native helpers or virtual machines. And we have here an example of a cluster of OpenShift deployed. And you will recognize those OpenShift control plane. These are the masters that I show you, the Kubernetes masters we've seen before. And then here we have the compute plane, which are the worker nodes where the applications and the containers will run. And from there, those containers and modernized applications can access through REST APIs to the REST Connect here, very close, in fact, to your existing environment here. But we can also have access to the containers running in a Z6 environment, for instance, you want to get access here. Or we can directly use management through the OSMF. When Adam discussed about the ZOS Cloud Broker, right, these are microservices running in OpenShift that helps you to deploy subsystems on the ZOS side. So I can provision a Kix region, a DB2, or an IMS environment, MQ, directly from my catalog running on the OpenShift environment, and integrating that into my dev test. Okay, so the ZOS container extension here is in fact a full address space running on the ZOS side, right? But you can execute Linux workload inside these environments. Okay, so when we are using, in fact, the ZOS container extension here, we are having this environment here, so an address space here, and inside this address space, we're using dynamic VPA here for the network environments, and we can deploy, you know, our workloads, which are Linux, a Docker engine, which is provided with the Z6 environment. Okay, so you don't have to install by yourself this layer. This is packaged within the Z6 environment, so it can be directly usable with an image for S390X. And we do have a lot of images today on S390X that could be deployed directly into your Z6 environment, directly inside the ZOS. Okay. So of course, these are some files right in the backend, and we can communicate, of course, with all the ZOS TCP IP stack. And to communicate, we can use a Docker CLI here to communicate and push, you know, those changes from an application point of view. What it means is that this solution here can be embedded directly within your DevOps pipeline, right? So to deploy your new applications on the form of the containers, this is one strong solution that you can use. Worth to mention, the Z6 workloads are all zip eligible, okay? So in terms of consumptions on the platform, right, that's something you can use. And in terms of benefits, right, clearly it's workload modernization, because you don't necessarily have to rewrite, right, or move some parts of your applications. You can just reuse existing applications which were maybe before deployed on x86, right, as front-end components. And you can say, those Linux workloads deployed on x86, I could bring them closer now on my ZOS and execute them inside the ZOS environment. So I'm taking all the benefits in terms of quality of service, workload management for all these applications, because they're running now part of my ZOS environment. Same thing for all disaster recovery and all the benefits you could think of, right? So that's really a very strong value proposal here for the co-location, quality of services, as well as for the operational efficiency, because you have all the processes from a ZOS point of view that you could reuse while taking benefits of all the modern developments with containers and microservices. Okay, so there are a number of use cases, right, that I will not detail here, but we already identified, you know, some points that helps to reduce the MIPS consumption, right? Some of the CPU processes are occurring today on ZOS, and using the Z6 technology, we could in fact offload or reduce some of this consumption on the MIPS side, because we're going to run some components inside the Z6 environment, right? MQ is an example, the service management is another example that we could have. There are also transfer between different systems. When you have a network and you have to exchange a lot of data between those systems, there are solutions today we can provide, like Aspera, for instance, solutions. And we could run some of this code inside the Z6 instance. So you're taking a huge bandwidth benefits, accelerating your transfer between different environments while taking benefits of the Z6 environment running on your ZOS environment. Okay. So in order to conclude this session here, we have identified a huge number of use cases, right, for these containerized workloads. Like I said, we were not before invited to the party. Today we can enter, right? This technology is not completely, of course, mature like some of them could be, because they are there for years and years, right? This technology is pretty new. So again, when we get into these environments, we really have to identify what kind of services we want to deploy, what are the criteria, and we are organizing workshops around those application modernizations choices, right? And we have, let's say, a guide or criteria on which technology finally to choose to deploy the application. Is it the HPVS one? Is it the Red Hat OpenShift one? Is this in fact Z6 or maybe potentially another kinds of technology, right? So 3 main use case: modernize, all the integrations with all APIs in new applications, and the last one is really on the consolidation place, where we want really to develop and build completely new applications on the platform. So that's all the capabilities for the container today. On the Z side, I wanted to open it to provide you, in fact, this view here about the platform. So thank you very much for your time.